Now I hesitated on that last problem because we were looking at aromatic compound, and I hesitated to say had a benzene ring because there are actually aromaticity is a property that many molecules could have that don't necessarily have benzene in them. But the reason why I thought it had benzene was because of the formula. I know there's at least 6 carbons, so it could be a benzene ring within this formula. So I sort of knew to start there. Well, let's talk about what aromaticity is. So there's this property that makes certain molecules more stable. And so when you look at benzene itself, there's no reaction because it's so stable. Okay, now we can have reactions of benzene, and that's what chapter 18 is about, but it's got to be different from alkenes. Alkenes are not conjugated necessarily. We saw in chapter 16 that you could have conjugated dienes, but they're going to have different reactions when you're even more conjugated. When we see a molecule like this, then you might think, well, what's the difference? You're adding a couple more carbons, but you also have conjugation here, so isn't this sort of like benzene? But you can see that there's actually a reaction in this case. So something's telling us then that this is more reactive than benzene is. So it's not really the same thing just to have conjugation doesn't mean that you're necessarily aromatic. And so this compound here, benzene, is aromatic. We don't necessarily see a reaction very easily here because of the stability, but here we see a reaction, so this actually tells me this is not as stable as benzene, and it's what we call non-aromatic. You can tell that the benzene is more stable because of its reluctance to react. All right, so how can we tell the difference between, if I don't have these data, so I don't know if things react or not, then how can I just look at a molecule and sort of predict that? So this is how I do it. I think of it as a certain number of requirements to gain or to have this property called aromaticity. All right, and you can see with benzene that benzene fits all of these. So number 1 is aromaticity, or this unusual stability that we see. It's usually with a cyclic compound like benzene. Okay, so cyclic, and it's got to be conjugated pi systems. So that means I've got pi electrons that are conjugated. Again, conjugated is sigma pi, sigma pi. So it's sort of this alternating pattern. And that leads to resonance delocalization. So that's why that's important. In order to have maximum delocalization, you want those p orbitals to be aligned to each other. So you need the molecule to be planar to allow for the p orbitals to align properly. So being planar is another requirement. So that means if I have groups on the molecule that twist it because of steric hindrance, and then the molecule is not able to be planar, then that's going to affect the delocalization. So it won't be as stable then. So you want to consider like the whole molecule. Aromatic compounds have a Hückel number. Hückel number is 4n plus 2 pi electrons. So if we look at 4n plus 2, basically what is n? It's just any whole number including 0. So if I have n equals 0, then I have 4 times 0 plus 2, so that's 0 plus 2. If I have n equals 1, then I have 4 plus 2, which is 6. If n equals 2, I have 8 plus 2 is 10, and so on and so forth. So just keep at, n equals 3, n equals 4. What we're doing here is, well, what is n? Why am I just choosing these? It just turns out that for numbers that fit this formula, where n equals 0, 1, 2, 3 integers, these number of pi electrons turn out to lend the molecule towards aromaticity. So the molecule becomes aromatic when it has these specific Hückel number of pi electrons. So what does that mean? I look at a molecule and I look at the number of pi electrons. So it could be lone pairs or it could be pi bonds, and they have to be conjugated, so every other bond. Okay, so here, pi, sigma, pi, sigma. All right, so then I look at this and I say 2, 4. So 2 pi electrons here and 2 more here. 2 pairs of pi electrons is 4 pi electrons. This molecule has 4 pi electrons. Is that a Hückel number? So I look over here and I'm like, well, we just did that analysis of all the Hückel numbers. 2, 6, 10, 14, da da da. Okay, so basically, it's not a Hückel number. Okay, we skip 4. So it's 2, skip 1, 6, skip 8, 10, skip 12, 14, skip 16, 18. So it's not a Hückel number, so it turns out that it's not aromatic. So that is a requirement, is it's got to have a certain number of pi electrons in the system. Okay, so let's go now to this one. 3 pairs of pi electrons, so that's 2, 4, 6. 6 pi electrons, is this aromatic? We know benzene's aromatic, but let's check. Here's a Hückel number is 6, so this works. So this is aromatic. Okay, and then here, how many pi electrons do we have here? We have 4 pairs, because each bond is a pair, so 4 bonds times 2 electrons each is 8 pi electrons. So clearly we're not going to have a Hückel number, so this is not aromatic either. And that's why, my friends, we did not see no reaction. We saw reaction here instead of no reaction, because this is not aromatic. It does not fit the Hückel rule. Okay? All right. Predict whether this compound should be aromatic. So this is a cyclic compound. It could be planar, and it looks conjugated. It looks like it has the pi sigma alternating pattern. So there is the possibility for delocalization all the way around the ring. Isn't that fun? Okay, I could do this all day, but I won't. Okay, I'll stop here. But anyway, let's count then. The only requirement left, it's cyclic, conjugated, it could be planar, or it might rotate out of plane. So let's see what happens. We'll find out about the Hückel number first. Does it have a Hückel number of pi electrons? So let's count. How many pi electrons do you see in this system? All right, so I see 22 pi electrons. That's 11 pi bonds, 22 pi electrons. And turns out if n equals 5, then I have 22. So this is a Hückel number, and what this tells me is that this molecule will be planar so that it can delocalize those electrons, thus will lead to an aromatic compound. So the answer is yes, it should be an aromatic compound. Now let's look at some molecules that don't have a Hückel number. What happens there? Okay, so this is cyclobutadiene. This compound does not have a Hückel number, and we did that example up here. It's got 4 pi electrons, 2 pi bonds times 2 is 4. Now, molecules with a 4n number of pi electrons, not 4n plus 2, that's Hückel, right? If it only has 4n, then that means that we're talking about numbers like 0, 4, 8, 12, 16, multiples of 4, okay? So if we have multiples of 4, then we don't see that they're stable. In fact, molecules with 4n number of pi electrons are actually destabilized. They are anti-aromatic. That's even worse than being non-aromatic. It's hard for this molecule to prevent conjugation because the rings strain and it's pretty planar, but it will still try to twist out of the plane. So it will, because it wants to avoid the conjugation. If it was planar, conjugated, and 4n pi electrons, that makes it anti-aromatic. So often molecules will try to get out of that so that they'll just be non-aromatic. All right, so I hope that makes sense. So therefore, this molecule is not stable when there's delocalization. So this molecule will do what it can to sort of twist out of plane. It can do that a little bit. So you can see where that instability comes from. It comes from the molecular orbital diagram for cyclobutadiene. So let's take a look at this molecule. If we do a Frost diagram, that means take the molecule and point it so that turn it so that one of its points is on the bottom. So here's my frost circle, and then I have this, and then these points here are here, and this point here is here. And then I start filling the diagram, 1, 2, 3, 4. And you can see these unpaired electrons want to be paired, so that leads to some instability for this molecule. Here's a step-by-step of how to do a frost diagram like I just did. For cyclic compounds, I know we've been practicing with acyclic compounds, like 1,3-butadiene. So when you have a cyclic compound and you want to do an MO diagram, you just twist it so that one point of that shape is at the bottom of the circle, so in the vertices, and then you want to make the shape of the orbitals go along with that, like that. Okay, so you can see that here. And then you can draw the dotted line through the center, and then you can start filling those with the pi electrons. And remember, just that line of symmetry in between, you can have antibonding on top and bonding MOs on the bottom. And if the symmetry went through the orbitals themselves, those orbitals would be the non-bonding MOs. So let's look at the diagram for benzene, and we'll answer the question, how many electrons are in bonding MOs? So first I'll do a Frost diagram. So I'm going to have energy levels here, like that. Okay, so I'm going to do this. So those are my molecular orbitals for benzene. This is my energy. So let's see here. I'm going to count for benzene how many pi electrons there are. So there's 6 pi electrons, 3 bonds. 1, 2, 3, 4, 5, 6. So 6. How many are in non-bonding molecular orbitals? Well, if I draw a line through the whole thing, I don't see any orbitals with that energy. So these are, technically there's no non-bonding MOs. There aren't any orbitals here, so I put a 0 here. Then how many are in antibonding MOs? So I don't see anything up here, so 0. And how many electrons are paired versus unpaired? So they're all paired. And that tells me, wow, that's pretty stable then. They're all pretty happy paired. We see 1, 3, 5, 7. Wow, what a name. Cyclooctatetraene. Okay, let's draw. What does that mean? Let's draw it. Okay, so this is our octagon. So we've got tetraene, cyclooctatetraene, so 8 in a ring. Based on this MO diagram, so basically we twisted this, put one edge on the bottom here, and then put the rest in here. And you can see that, do you think this will be aromatic? Okay, so taking a look here, we see that these bonding MOs are filled, but we see that the non-bonding MOs are unpaired here. So that's going to lead to some instability. So I would say that no, I would not expect this to be aromatic. And in fact, we see that it has 4n pi electrons. So it will do what it can. It's a large enough ring that it can bend out of plane. So it will avoid being anti-aromatic by bending out of plane, so it doesn't conjugate all 4n electrons. So it will be what we call non-aromatic. If it was small, like cyclobutadiene here, and it couldn't twist very much, then that forced conjugation would make it anti-aromatic. So now looking at this molecule, it's cyclic, it's pretty planar, it's small, so it can't really bend or twist too much. So how many pi electrons does it have? I think we just see that one double bond right here, so that pi bond. So that's 2 pi electrons. So just ask yourself, is that a Hückel number? And it is, because if n equals 0, then 2 pi electrons is a Hückel number. So that means that it satisfies all the requirements of being aromatic. And this positive charge, you might be wondering about it, it just means that there's an empty p orbital here. So what that does is it's full right here from the pi bond, but it can spread that out to that empty p orbital. And how do I know that? I just use resonance to figure that out. So let me show you my secret. My secret is I can move this over here, and I can show that positive charge around the ring. So that means that there is delocalization. So then I know it's conjugated. Let's try then using that example to try some of these on our own. Okay, so first figure out is it cyclic, is it conjugated system, how many pi electrons are in the system. If it's a Hückel number, it's aromatic. If it's not, it could either be non-aromatic or anti-aromatic. So let's go through and see if you can figure this out. All right, so for the first one, I see that there is conjugation, but these count, because they can resonate in, they could count as part of the pi system. So if they do, then that's 2 pi electrons plus 2 pi electrons is 4 pi electrons. That's an anti-aromatic number. Remember, any multiple of 4 is anti-aromatic. And because this is a small ring, it has a hard time sort of twisting out of plane. So because it can't twist very well out of plane, it forces these pi electrons to be in conjugation. So that will mean this is going to, unfortunately, be anti-aromatic. All right, we saw with the previous example up here that this kind of cyclopropenium ion is actually pretty stable because it's got the 2 pi Hückel number, and so this is going to be aromatic. And I can check to make sure there's conjugation. There's definitely resonance delocalization here. For this one, I also see some delocalization, but I only see 4 pi electrons, 2, 4. So this 2 would be anti-aromatic. And this molecule, because it's positive here, it's forced to have this hybridization of sp2, so that lends itself for conjugation here even when it would prefer not to. So this is still considered anti-aromatic, and the molecule might try to bend out of plane, but it's conjugated because of the hybridization there. And then this one here, so this clearly this lone pair here could either be part of the pi system or not. So let's find out if it wants to be or not. 2, 4, 6, 8. So if we include this, it'll be 10. And 10 is a Hückel number where n equals 2. So 4 times 2 plus 2 is 10. So this is aromatic as long as this lone pair participates. And it looks like it can because it's we could push the electrons. And this is one way to check, is if you can push them all the way around and come up with a resonance structure, you can tell that they're conjugated. So aromaticity can also explain why certain hydrogens are more acidic than others. When we look at this molecule here, you see the hydrogens that are gray being abstracted, but there's also hydrogens here, if you recall, there's these sp2 hydrogens, and they're not being taken off, okay? So you might wonder, why is that? And that's because these positions here are leaving you with this lone pair, okay? So if you take one of those, it leaves you with a lone pair here. And that's in conjugation with these pi bonds. So that allows you to have a possibility for aromaticity. And we see that in this case because it's a Hückel number, 6 pi electrons, if these are conjugated, and it's conjugated. So that aromaticity stabilizes this conjugate base, which means that when you remove these H's are actually the acidic ones, not these right here. And again, you can check that by removing the other hydrogens, and you'll see that this is not aromatic, but this one is. So that makes these hydrogens that are gray much more acidic than the ones that are in red.